Good morning, my dear students. I hope you feel well. Today, I'm going to continue my explanation about the nature and the propagation of nervous information part 2. The objectives that must be covered today are how to define the action potential and how to identify the different parts of the action potential. At the beginning, and to refresh your memory in relation to the origin of resting potential, I will remind you with the following facts. The higher membrane permeability to K+ ions than to Na+ ions, and the unequal distribution of ions between extracellular medium where Na+ ions dominate and intracellular medium where K+ ions dominate. Basically, these two facts are responsible for this membrane potential, which is called the resting membrane potential of -70 millivolt. Basically, the neuron can react to many stimuli of different nature, such as light, sound, heat, pressure, and so on. That is why it is an excitable cell. The resting potential is easily disturbed or modified by stimulation. This modification causes or initiates a nerve message, an action potential, which travels along the neuron. And here comes up the central question: what is an action potential and how is it a trigger? Of course, an action potential is the result of a very rapid rise and fall in voltage across a cellular membrane, with every action potential or impulse similar in size. And to emphasize more about that definition, we should say that an action potential requires an influx or inflow of positive sodium ions to produce a specific change in voltage known as the threshold value. Here we have a video that helps us to understand the action potential more. In order to interpret electrically the phases of action potential, we must demonstrate the following. At the beginning, an effective stimulation, which is of a threshold level or above, must be applied to open sodium channels in the membrane of the neuron. Such opening leads to inflow of sodium ions to make the interior more electropositive. This is known as depolarization. When the voltage reaches +40 millivolts, sodium channels close and potassium channels open to permit the outflow of potassium ions in order to make the interior electronegative, and this is known as repolarization. Finally, a delay in closing the potassium ion channels permits the continuous outflow or exiting of more K+ ions to make the interior even more electronegative. This is known as hyperpolarization. Now, watch the video.
During an action potential, voltage-gated channels open and close, altering the permeability of the plasma membrane to sodium and potassium ions. A threshold stimulus changes the shape of the voltage-gated sodium channels, causing their activation gates to open. This event marks the beginning of phase 1 of the action potential, known as depolarization. As sodium ions diffuse into the axon, the membrane potential becomes less negative. This causes more voltage-gated sodium channels to open, and the membrane potential soars to plus 30 millivolts. At this point, two key events occur. The inactivation gates of voltage-gated sodium channels close, and voltage-gated potassium channels open. These two events mark the beginning of phase 2 of the action potential, known as repolarization. As potassium ions diffuse out of the axon, the membrane potential becomes negative again. However, the membrane potential continues in the negative direction, going beyond the resting state of minus 70 millivolts. This marks the beginning of phase 3 of the action potential, known as hyperpolarization. During this phase, voltage-gated potassium channels close and all voltage-gated sodium channels are released from inactivation. By the end of this phase, ions move through leak channels only, and the membrane potential returns to the resting state of minus 70 millivolts. The neuron is now ready to fire another action potential. Summary: generation of an action potential. A threshold stimulus opens voltage-gated sodium channels. Sodium ions diffuse into the axon, depolarizing it to plus 30 millivolts. Voltage-gated sodium channels close, and voltage-gated potassium channels open. Potassium ions diffuse out of the axon, repolarizing it to a negative value. The membrane potential briefly hyperpolarizes. Voltage-gated potassium channels close, and the membrane returns to the resting state of minus 70 millivolts.
This is the action potential, and these are the phases of the action potential.